In this section, we will focus on a physical implementation of quantum bits, qubits, and we will discuss how they behave and how they can be operated. The goal is to understand the connection between a physical qubit and its mathematical representation as a basis to start programming quantum circuits. Although the specific physics really depends on the qubit implementation, the overall principles of quantum operation are rather generic. While you may not need to understand all the relevant physics aspects in order to design a future quantum application using high-level language, I highly encourage you to also study the lowest level of the qubits themselves to appreciate the challenges and the opportunities in scaling qubits to a fault-tolerant quantum computer. Moreover, if you want to deepen your knowledge on qubit operation, this is a good place to start. Furthermore, QTech has its own quantum chips that you can program yourself over the cloud using the Quantum Inspire interface. Quantum Inspire is unique by offering multiple qubit technologies, such as semiconductor spin qubits and superconducting gate-model qubits. You can simply make an account and directly start to program. But first, let's focus on the physics behind these qubits. The prototypical qubit is the electron spin. The quantum mechanical spin states of an electron split in a magnetic field due to the Zeeman interaction. In a magnetic field, there are states spin up and spin down, and these are separated by the Zeeman energy. And we can define qubit states on this physical qubit. When the electron is in one of the basis states, so spin up or spin down, the qubit state is in the corresponding state 0 or 1. Note that from a physics perspective, we define the lowest energy state as the spin down state, while in information theory, this state is labeled as the state 1. These definite states are the classical states. But a qubit can also be in a superposition state, a superposition of one of these basis states. Now, regarding the physical qubit, this corresponds to the electron spin being in a superposition state of spin up and spin down. Note that this is not just a combination of the two, like a needle that's pointing in some direction. It can really be in a quantum mechanical superposition. Next, we will see the effects of the magnetic field on the spin qubit. Let's first get some feeling for typical values. In spin qubit experiments, we usually apply magnetic fields of order 1 Tesla. Now, as a reference, Earth's magnetic field is several tenths of microtesla. Thus, we often need relatively strong magnets when working with spin qubits. But even permanent magnets may generate these fields. For a G-factor of 2, a magnetic field of 1 Tesla results in an energy of 116 microelectron volt. In frequency, this corresponds to 28 GHz. Now, what does this frequency mean? Over time, the spin-up state will acquire a phase relative to the spin-down state, exactly with this frequency, which is called the Larmor frequency. This means that when the qubit is in a superposition, thus the electron spin is in a superposition of spin up and spin down, a phase is accumulating over time. And this phase is very important. If we want to execute quantum algorithms, and we are applying operation after operation, it is crucial to keep track over the phase. Thus, we need to keep track over this phase with great precision in order to do a high-fidelity qubit operation. So if we don't do so, we lose the phase information, meaning that the qubit will decohere over time. The loss of information may be the result of the clock in our equipment not being perfect. Thus we think we know the phase, but due to the imprecision of our instruments, we are off. Our inability of determining the frequency is not perfect. It can also be the result of noise. This noise can come from the qubit device, but it could also come from the outside world. For example, the magnet that we use to create a magnetic field may fluctuate over time. These fluctuations in the magnetic field will change the Larmor frequency, and thus will result in a phase that fluctuates over time. Indeed, there are many factors that need to be under control in a quantum experiment. Fortunately, we have learned in the last decade how to do that very well. Let's now focus on how to control electrons with the precision needed for quantum computing. First, we want to isolate electrons such that we can control them. Excellent way of doing that is by making use of solid-state systems. Let's consider a semiconducting material. The electrons in a semiconductor interact with the lattice in such a way that there are bands in energy where electrons can be placed, separated by gaps in energy where no electron states are available. In a semiconductor, all energy states are filled such that the Fermi energy is inside the band gap. The first band above the band gap is called the conduction band, while the band below is called the valence bands. Charge carriers in the conduction band are called electrons, while the charge carriers in the valence band are called holes. The reason for this labeling is that the dispersion, the relation between energy and the momentum, is negative for the valence band, which gives rise to a negative mass. Indeed, the interactions of an electron with the lattice results in quasi-particles that have a different behavior from an electron in vacuum. But this also means that by tuning and controlling the parameters that determine the interaction, for example the separation between atoms, we can engineer the properties of an electron. And this is the key to the design of optimal qubit parameters. It's also for this reason that various materials are being explored as a platform for quantum information. Gallium arsenide heterostructures offer an extremely low disordered interface, where electrons can travel over long length scales before scattering takes place. And this has been one of the main reasons why gallium arsenide has been the driving force behind semiconductor quantum dots for a long time. Unfortunately, gallium arsenide is also a material with a large abundance of nuclear spins. These nuclear spins fluctuate over time and can interact with an electron residing in a gallium arsenide quantum dot. This interaction is called a hyperfine interaction, and it affects the resonance frequency. Thus, the nuclear spin fluctuations will quickly result in an unknown phase. Indeed, there are many factors relevant in determining the phase stability. But fortunately, there are also ways to resolve this. The most effective way is to use a material without these nuclear spins. Many group 4 materials contain isotopes with an even amount of nuclear spins, such that there is no net spin interaction. And that is why carbon or diamond, silicon and germanium are all being studied for quantum information. Interestingly, silicon and germanium are also the semiconductors that are being used by advanced semiconductor manufacturing to engineer the technology behind our information age. Indeed, using the technology that is used to build transistors, by far the most replicated man-made structure to build qubits, is highly promising for scalable quantum technology. With that in mind, silicon has become a leading material for semiconductor quantum computation. Heterostructures of silicon and germanium are engineered to provide an excellent interface where electrons can be confined in the presence of low disorder and where there is no detrimental nuclear spin interaction to build excellent qubits. While isotopic purification is perhaps the most effective way to reduce hyperfine noise, there are also other means. The main reason for hyperfine noise is the overlap of the wave function of the electron spin qubit with the nuclei. Now, by making use of holes instead of electrons, this interaction is heavily reduced. Holes are described by a p-wave function, and as a result, the overlap vanishes. However, next to contact hyperfine interaction, there can also be other interactions, such as dipole-dipole interactions. And while their influence may be minimized by choosing cleverly the magnetic field direction, finite dephasing due to nuclear spins remain. But fortunately, purified silicon and germanium can be made rather straightforward by industry. To give you an example of the status of the field, here you see a 300mm silicon wafer processed by the industry using the same techniques applied to make wafers for electronic applications. And what's special here is that not natural silicon is used, but silicon containing virtually only the silicon-28 isotope. Isotope with no nuclear spin, which results in the absence of nuclear spin interaction. And as we will see later, the absence of this nuclear spin interaction causes the Larmor frequency to be very stable in time, providing extremely long quantum coherence for electrons.